the Hangout link? Oh, it's already started. Okay. All right. Well, while I would like to take credit for being the chief architect of the network group at Intel, I'm not the chief architect, unfortunately. I am an architect in Intel's data center group, in the network platforms group, which does all of Intel's. It's basically Intel networking. I am on the data packet processing team, which specializes in very high throughput, low latency network applications and doing whatever we can to accelerate those.
Can you repeat louder, please?
Yes, yes, I will. Is this better?
Louder. Turn the volume on.
Any better now?
Not quite yet.
Okay, I'll just talk louder. How about that? Okay, so if we get to our legal disclaimer here, which, whatever. The one. Hey, I'm an engineer. I'm not a lawyer. You might be wondering why Intel cares about containers. When I go to conferences, when I go to DockerCon or ContainerCon or whatever, I get asked all the time, why is Intel even here? The answer is because everybody else cares about containers, and people that run data centers are our customers. So my agenda for today is why Intel cares about containers. Go into a little bit more depth about that. Making containers run best on the Intel platform. Solving problems in the container ecosystem. Containers are great, but they do have some problems. Standardizing the technology. Right now it's kind of a Wild West field in the container ecosystem. Contributing to open source projects and applications of containers outside the cloud and the data center. So to go back to why Intel cares about containers, this technology is being deployed across the globe in data centers all over the place, whether it's cloud providers or your standard enterprise data center. People are using them en masse. Those that aren't using them are making plans to start using them in the near future. So they're becoming pervasive across the globe. And Intel specializes in creating technologies for the data center, especially my group. Not just the cloud, but enterprise data centers, telecommunications data centers. And we try to look at things that run the internet. So in order to further container technology and what Intel's doing with that, we are trying to make them run as fast as possible on the internet, on the Intel architecture platform. We are trying to solve problems. We are trying to establish and proliferate standards across the ecosystem. And we're trying to progress open source projects. Any questions so far? Okay, that should be uppercase. Okay, so making containers run best on Intel architecture. There's four main technologies that we're employing here. Technologies that you already have, if you have something past Sandy Bridge. That would be Intel virtualization technology. That's VTX, VTD, and VTC. If you're familiar with what those are, that's virtualization technology for execution, for devices, and for connectivity. The next is the Intel Resource Director technology, which is fairly recent. That came out with our Broadwell chips this year. And then Quick Assist technology and the Data Plane Development Kit. How many people here have heard of DPDK? Okay, how many here use it? Okay. I was a little curious because sometimes we find that people outside of the telecommunications industry have never heard of it or don't see a need for it. whereas people in telecoms tend to find it very useful. So there's two main things that we would do with virtualization technology here for the network. The first one is virtual machine device queues, VMDQ. What this does is it offloads certain ring buffers onto hardware. Ring buffers in the TCP/IP stack. These are mainly the TX and RX queue. There are some other queues that are offloads as well, but it's mainly TX, RX. What this does in the virtual machine world is it allows you to take that functionality, those buffers and the CPU cycles that you spend servicing those buffers from the TCP/IP stack and push it down into the CPU and the NIC. What we're doing is to enable that. Can you hear me better? Nice. What we're doing with containers is to enable those device queues to be used on a per container basis, so that the vhost NIC that you use to tunnel down to your virtual switch, whether it's your Docker 0 device or whether it's an OBS instance or whatever, those queues are offloaded per container. They know about namespaces, and they're offloaded onto the VMDQ. We think that will free up CPU cycles and allow you to get better density on the box that way. The second thing that we're doing is SRIOV. SRIOV has been around for quite some time. It's implemented by multiple vendors. What this does is it creates a virtual NIC. It's actually a virtual function that is attached to a physical function on the NIC that allows network traffic to pass straight through the kernel down to the hardware and then gets switched on the hardware. It's used very much or very extensively in virtual machines, but not too many people use it for containers. Now there is an SRIOV plugin for libnetwork that was developed recently. What we're doing is trying to enable SRIOV for the entire container ecosystem. Of course, running in the Intel drivers and all that. And that is already available in most Intel server NICs. If you buy a server that's got an Intel chipset on it, most likely it's going to have a NIC that supports SRIOV. Questions?
Question. SRIOV, like today, can assign those virtual function to per VM. Can you do some similar thing to the container?
Yeah, well, it depends. So in a container landscape, normally with SRIOV, you have to tell the system how many devices you need at startup. You have to pre-allocate them. Then the hypervisor will assign those devices to VMs that need them. With containers, you get a lot greater density there. So you have to pre-allocate all of your SRIOV virtual functions at startup, all of your possible SRIOV virtual functions at startup. So what we're trying to do is trying to enable container execution engines like Docker, like Rocket, like LXC, to be able to say automatically, without a plugin or anything, just assign this SRIOV endpoint to a container. Not only that, but if that container is running inside a virtual machine, we want that SRIOV endpoint to be able to go all the way through from the container to the virtual machine kernel to the hypervisor and then out to the NIC without any problems.
So containers are, if you get familiar, they are like cattle, right? So does that pose a problem because they'll be scaling up and down as per need fairly fast?
Yes, that does pose a problem. In Intel NICs, at least, you have a limited number of virtual functions. It ranges, depending on the model you have, between 64 and 256 virtual functions. So if you have a box with, say, 1,000 containers on it, obviously you can't have all of your containers use an SRIOV endpoint. So there's two approaches we're taking. For the cattle scenario, in which your workload across your box is homogeneous, your containers are largely doing the same thing, or the load that they're putting on the system is roughly similar, we're looking at taking SRIOV endpoints and aggregating them into proxies that can talk amongst themselves within the switch. Don't know how that's going to work. We don't think that'll scale very well. So what we're looking at primarily for SRLB are container deployments with heterogeneous workloads in which some containers are doing more work than others on the same box. For instance, say a container, say you're running a web server, database server, and some application to serve as middleware between them. And for whatever reason, your database server is communicating more frequently on the network than others. In that case, you would assign that container an SRLB endpoint and use something like VMDQ for the other containers. Did that answer your question?
So is the middle point which is assigning the SRLB, it's a software layer that we're talking about?
Yeah, in this case, now, as I mentioned, there's a lib network plugin for doing this. What we're trying to do is kind of standardize the semantics for saying this container gets an SRLB endpoint and this container doesn't.
So
So one more thing, if it's difficult to know a priori which containers will be maybe hogging the network bandwidth, then that's difficult to do, right? Design a virtual function.
Right, to figure out who's hogging the network and who's
No,
not.
if it's difficult to know what a priori, which container will be hogging the network or which will have high network needs, then that poses a problem.
Right, yeah. I mean, the only way to determine before you start a container whether it's going to hog the network or not would be through the use of labels or some sort of metadata system.
and RDP could do that also, right?
Yes, yes.
Resources.
And I'll get into in a few minutes. I'll get into how we're trying to use telemetry to make those decisions a little easier.
If you're passing a VF through a container, you need to have IOSM support from it. You assume there's process address space ID support, the user space level. Is there an assumption on the hardware?
I'm sorry, say that again?
If you're passing a VF through to a container, you need appropriate IOSM support. Either it will contain a single block or it will segregate among the various processes within a container. So do you assume passive support at SRIOV level?
Yeah, well, so for
Can you repeat the question?
Oh, yes. Yes, he's asking about PASID support. PASID is Process Address Space Identifiers. What PASID does is it establishes well, for lack of a better term, namespaces for queues inside the NIC to assign virtual functions to divvy up memory so that DMA addressing inside processes can be sliced up inside the NIC. So that imagine a space in which you have 500 containers and they're all trying to address the same DMA block to talk to a network interface card. That can cause a contention, it can cause a variety of other things. So what PASID does is it says, this chunk of DMA belongs to this process ID and this chunk of DMA belongs to this process ID. And then you can further allocate virtual functions or virtual NICs through SRLV to these address blocks. So we are looking at PASID. We're developing PASID support for some of our future NIC offerings. As are a lot of people in industry. We're looking at PASID more for the VMDQ style offloads than for the SRLV, the use case. We're looking at it for more of a homogeneous deployment than a heterogeneous deployment, as I mentioned earlier. Does that answer your question? Okay. Any more? Okay, so Resource Director Technology came out in the Broadwell chips, I think, a few months ago. And what RDT does is it's a basket of technologies that includes cache monitoring technology, which tells you what pressures you're experiencing on your L3 cache, what processes are using it the most, what processes are using it the least. You have your cache allocation technology, which lets you dynamically change the amount of L3 cache that's available to processes. You have your memory bandwidth monitoring technology, which tells you what processes are using the most memory bandwidth compared to others. And then there's a fourth one which escapes me right now. Anyway, as a basket, RDT allows you to dynamically not only monitor but change the use of cache and memory on the system. In this case, we've identified two potential ways to use this in a heterogeneous environment. One is to take a container that you know will be using the system resources more heavily than others. Say it is a very large, very powerful database or a mission-critical telecommunications application or whatever. You could use RDT to ensure that that process, that container,
You can see the slides in the handout.
RDT can allow you to give more cache and give more memory bandwidth to processes, the containers that need it. Not only that, but it can help you to detect and isolate noisy neighbors within a dense container environment. If a container is using too much memory, too much L3 cache, if it's accessing L3 cache too often, you can detect that and gradually scale it down until it's forced to go to main memory for its storage.
So how do you change, how do you monitor, what tools do you use to monitor cache utilization? You can all do that, or do you need separate tools?
The tools for that would mainly, I'm sorry?
Repeat it.
Oh, yes. He's asking what tools you would use to manipulate and monitor the cache and memory. Right now, in the current incarnation of RDT, those tools are expected to mainly be the kernel. We're expecting the kernel scheduler to be the primary user of that. In future RDT deployments, we may be creating some additional user-line tools to allow system administrators to look at that. What we're doing for containers is to allow tools like Kubernetes to use it as well. We want to create a feedback loop using RDT and some other technologies to pull performance data out of the system and push it up to Kubernetes to say things like, well, this container here is too noisy. It needs to be moved to a box with more resources so that it can use that more effectively. Or I have a container that's using a lot more RAM than I thought it would, so move it to a box that has whatever resources it needs to do its thing better. Okay, and Quick Assist technology has been around since Sandy Bridge, so it's been a while. It's integrated into our chipsets, and it also is in a few standalone PCIe card devices. And this is basically a crypto and compression offload. And what we're doing with containers in this regard is to make sure that QAT can be used in a very dense container environment without overloading it, basically. We're trying to enable the kernel and the container ecosystem to be able to use it effectively for containers. We've done that for virtual machines, and we know it works for containers, but we don't know how it scales for containers yet, so we're just working to ensure that it does scale well for that. And insofar as the DPDK goes, if you're not familiar with it, the DPDK is a software library that creates a fast data path from the user space directly to the NIC. When you use a TCP/IP stack or even a raw socket on an Ethernet device in Linux, you still have to make system calls, and you still have to make copies and various under other things that inhibits the performance of very high throughput network applications. So DPDK seeks to eliminate system calls, run its own maintain its own ring buffers, maintain its own polar, and a variety of other things, limit copies, so that we can accelerate throughput through the library directly to the NIC to be as fast as possible. Right now, it is faster than the Linux kernel. It's already being used by a great number of people in the telecommunications space. It is integrated with Open Virtual Switch, so if you want to, you can go and download DPDK and ODS and run it on a Linux box and have a user space instance of Open Virtual Switch that you can talk to. And while it is cross-architecture, there's a number of different ports for it. It's extremely highly tuned for the Intel architecture. And what we're doing with DPDK is to try to create an environment in which you can use DPDK to create a service chain or a composable microservices application for high throughput, low latency telecommunications apps. What we're aiming to do there is to use DPDK instead of going up and down between the NIC and the container. You use DPDK to go all the way through your service chain in user space. And doing that, we hope to achieve not only line rate, but line rate on multiple 40 gig cards. So that is a work in progress right now.
Question. What version of the DPDK supports this container?
I'm sorry?
Which version of the DPDK?
That will be the next one. I think it's 1607 is out now. The initial support for containers will be out for the next few months.
Oh, it's not released.
1611.
It's not released yet, no.
We have Vertile for containers released in 1607.
Yes, we do. We do have Verd.io, but we have Verd.io, and we made some changes to DPDK such that if you want to use the DPDK library with a polar inside of a container, DPDK doesn't inhibit your startup or shutdown time. Because the way DPDK is created, it wants to own a processor and own it forever once it's started, which makes containers, the promise of millisecond startup time, shutdown time, it kind of breaks that. So we've done some work in the release version of DPDK to limit the amount of time it takes it to start up and shut down. And we have implemented Verd.io support. But the rest of the support, the microservices, proof of concept that we're working on, and some other things that we're trying to support, SRIV for containers, for instance, will be out until the next release.
But currently it supports only a pole mode, right? If you're using a pole mode in the container, it's like continuously CPU cycles.
Mm-hmm. Right now, yeah, the Verd.io is only implemented in the PMD, which means you burn a core for it.
So in the containers, they're going to modify that one.
Yes. Mm-hmm.
We have it in the past to also support the interrupt mode, right?
The what?
The interrupt mode for the next. The interrupt mode.
Interrupt mode.
Yeah, in addition to PMD, I think it is there on the
No,
roadmap.
currently it's not available.
Yeah, it is not available, but it's on the roadmap.
Yes, in the roadmap, yes.
Yeah, we have many things on the roadmap. Many things. And even more since the summit last week.
So what's this Verd.io?
Verd.io is an operation mode for network interfaces and drives, other things, basically devices in virtual machines that's para-virtualized. It knows it's running on a virtual machine, so it can make some assumptions about what it's doing, which it makes it faster, essentially. It talks directly to the hypervisor, and then over time, Verd.io support has been pushed down into the hardware, and currently, Verd.io is considered one of the faster ways of doing things in virtual machine mode. Okay, solving problems. These are the problems, the 5 main problems we see as existing in the container ecosystem. The first one is lack of memory isolation for multi-tenant environments. That means if you say you're running a data center with company A and company B as tenants in that data center, and both of them are fierce competitors, and one of your containers gets compromised by an attacker, if the attacker gets privilege escalation, that they have access to the host kernel. Because containers all share the same kernel, that means all of your containers are vulnerable to the attacker now. If they did not share the same memory space, however, that would not be quite as possible. The next one is lack of policy monitoring and enforcement capability. Some of us have to guarantee things like this application will not perform in anything more than 5 milliseconds on the network. Or this application will use no more than 1 core on the system. And right now, it's very difficult to set up a scenario in which a dense container environment will allow you to guarantee those SLAs.
Sorry, the slide was not moving on that handout.
Oh, okay. Is it updated now?
No, it still shows the previous slide.
Okay. Well, I'll keep talking.
Yeah.
While there's been a lot of work going on in the OpenStack community regarding containers, especially with the Magnum and the Courier projects, they're not finished yet. And we consider support for containers in OpenStack environments to still be in the nascent stage. So we're contributing some manpower to further that along. Poor support for very high throughput or low latency applications right now. Because you get the density that you get with containers, that means you have a lot more contention on your network hardware, which means we don't know if you really need to push a lot of data through a box. We don't know if containers can do that in a lot of cases. It depends on the application, but in many times the effort that has gone into optimizing virtual machines for high throughput applications hasn't necessarily been reflected in the container world. Are we good?
Yeah.
Okay. That and data plane networking and storage is often an afterthought in the container world. You go to DockerCon and you talk to companies like Portworx or some of the other, I'm sorry? Yeah, Cluster HQ. A lot of companies will tell you, I don't know why people aren't talking about storage or these things. It's not that people don't care, it's just that getting the container ecosystem going and in a stable state before they go into talking about things like storage, distributed storage and things like that seems to be more important. So we want to kind of further efforts in these areas of the container ecosystem that are kind of not as well addressed as they could be. So how many of you have heard of clear containers? I didn't expect many of you would. Clear Containers is an experiment at Intel to use our VTX technology to create memory isolation for containers. And this memory isolation means that you get greater security in multi-tenant environments. It'll support the advantages of the container model, the density and the scale, without compromising this security aspect. Now, what clear containers are is they're not containers at all. They're very, very, very lightweight virtual machines that behave like containers. When I say very, very lightweight, I mean they don't have a BIOS, they don't have any hardware that they might use in a shared environment other than the NIC, storage, the very bare essentials. They don't have a post cycle. They don't have a lot of things a normal virtual machine would have. And because of this, we get much greater density than with virtual machines. The 2 orders of magnitude greater density than, in fact. So this is this looks a lot like virtual machines right here. These are supposed to be clear containers. They each have their own kernel, which is actually a part of a kernel, attached to the kernel underneath, their own middleware and their own application. The thing is that they're all orchestrated with Docker and Rocket, and Kubernetes for that matter. And I say we're working on that. But right now we have branches for Docker and for Rocket that allow you to instantiate clear containers alongside normal containers if you need that kind of security and memory isolation for those particular containers. We are working on embedding clear containers inside of Docker images and Rocket images such that they're portable, and integrating it with Kubernetes so that when you say, I want to spin up a container over here, but it needs to be isolated, you can tell Kubernetes, I want it to be a clear container. Kubernetes will be able to tell Docker it has to be a clear container and instantiate it there as a clear container, as opposed to a normal Linux namespace container.
Now that you've brought that up, what's your time frame for release?
We've already released clear containers.
I mean, for release of the technology as you identified it.
As I identified it.
In other words, to establish the clear container image within these other container environments and allow them to therefore exist in an isolated fashion.
I don't know.
Fair enough.
Yeah.
I had to ask the question after you brought it up.
Yes, we do have a roadmap, but it is not a public roadmap right now. And I can't speak to when we'll have a release.
Fair enough.
Sorry.
Question?
So,
You go first.
so this looks fundamentally like a VM. I thought clear containers were native Linux containers, like.
Clear containers are virtual machines.
Right.
As a matter of fact, they are launched by KVM or QEMU, whichever you.
So does that mean that we definitely need a hypervisor on the box? It's just not going to run on a plain vanilla Linux kernel,
No, it won't run on vanilla Linux kernel.
like even 4.1 the later versions, like
I believe you'll have to have KVM, QEMU.
Okay, so we just can't just install Docker and it's not.
No, you can't just install Docker.
So my question related to this, since this is just like a VM, right? So how the resource partition get arranged? Like container, we know that you can dynamically change the CPU, memory, number of processor, while not number of processor is you see all the processor. While VM you see, like I give you 4 processor or 2 processor, and unless you reboot, normally you don't see that. So how does the memory resource partition work? CPU, memory, CPU one need number of processor,
Right.
and memory.
I don't know the technical details, but the kernel that runs inside of each container is very aware of the kernel underneath it. So the NUMA topology of the host machine that it's running on is exposed to the clear container. I'm not sure how flexible the tools are right now in being able to say, run this on 1 processor, run this on 2 processors. But I do know that the awareness of the host system is much greater in clear containers than it is for virtual machines.
Is that also true for the memory? Like just like think about the normal virtual machine where you run, I give it 8 gig, and later all of a sudden you change it to 12 gig or 6 gig. Does that work?
Right, yeah. I would have to get back to you on that.
So one deployment model is to put containers inside a VM. So kind of put clear containers inside a regular VM. If you did that, would there be nested virtualization?
Would there be what?
Would there be nested virtualization with additional support virtualization?
Yes, actually, nested containers is another thing we're interested in working on just across the board with regular containers and with clear containers. That is on the roadmap, but I couldn't say when it'll be implemented.
How about nested containers? Can you put these inside a regular virtual machine?
Oh, yeah, of course, yes. Yeah, I'm sorry.
You are repeating the question and
Oh.
not.
Yes, I'm sorry, I'm so horrible about that. The question was, can you put clear containers inside a virtual machine? And yes, you absolutely can.
Can you run clear containers inside clear containers?
That was the question that I answered.
Oh, I'm sorry. I didn't.
Yeah, we're working on it.
Nested containers, right?
Yes. Yeah, nested containers is actually kind of a big deal for some people. Not everybody, but for some people. And it poses some interesting problems, especially when you start talking about VXLAN and things like that. Okay, so telemetry and orchestration, telemetry for orchestration and management. We're exposing information about the platform to the chips, from the chipset, the CPU, and the NIC to the kernel. That means pushing performance metrics, sensor data, network telemetry to the kernel, and then from the kernel up to Kubernetes so that the orchestrator can make better, more informed decisions about where to put containers. We've developed a tool called Snap. I meant to put a logo of it up here. It's written in Go, and it's highly integrated with Kubernetes. I believe it's being deployed in a variety of places right now. But the purpose of Go is to be the agent that pushes all of these metrics up from the system to Kubernetes. And our hope is that we can use that to provide the information necessary to meet SLAs. And when coupled with RDT, that gives Kubernetes a view into the system that it doesn't currently have right now. In addition to that, we're looking at blockchain technology, which is known as the distributed ledger system for Bitcoin. We're backing blockchain technology in our Internet of Things group, but we're looking at using it to be yet another mechanism for exposing this enhanced platform awareness data from the system up to orchestrators like Kubernetes.
How are you looking at your implementation of that? Are you looking to have that available as a service so that it becomes at least a secure, known set of participants, or can it be defined by the individual who's utilizing it?
Well, right now the blockchain, or you're speaking of blockchain in specific?
I'm speaking of it in terms of the way that you're looking at implementing it.
Okay, the question was, how are we implementing blockchain? Are we going to expose it as a service or something else? Right now, our investment in blockchain is as a contributor to the Hyperchain project. I think it's a project. In the form of a framework that you can use to deploy distributed ledgers. So right now it exists more as an API than anything. And I don't know what the plans are for doing that in the future. I don't know if we're going to be developing it as a service or not. And then there's OpenStack integration. We're actively working on the OpenStack Magnum and Courier projects. We started off doing the same thing that Courier was intended to do, trying to avoid the double encapsulation problem with things like VXLAN. But that's gone into us directly contributing patches, bug fixes, things like that to both the Magnum and the Courier projects. And then we developed Stackinettes, which is a containerized OpenStack. It lets you deploy OpenStack in containers so that you don't have to go through the headache of actually setting up an entire OpenStack infrastructure. And we've actually developed a cluster that runs Stackinettes in which Kubernetes deploys OpenStack inside containers, which spin up VMs that then spin containers up inside those VMs. So it's containers and virtual machines in containers.
So you're running Kubernetes inside the container?
We are using Kubernetes to orchestrate both VMs and containers.
Yeah, okay.
And the reason we did that, when I first heard about this project, I was like, you're doing what? But when you think about it, it kind of makes sense. It makes OpenStack deployments easier to roll, and it gives you a little bit of high availability when you start thinking about the Kubernetes service proxy and things like that.
Question. So for the case you mentioned to create a container inside VM, inside a container, I guess the first two layer of VM, container to VM, that's one-to-one, and I assume VM to container, that's one-to-many.
The VM to container would be one-to-one as well, I believe.
Oh, the whole thing is a container to VM to container, one-to-one-to-one.
Oh, no. It's container to VM is one-to-one.
Okay.
VM to container would be one-to-many.
Yes, okay, that's what I mean. Okay, good.
Yeah.
Got it.
And then I've already talked about DBDK and fast data paths. I guess this slide is kind of redundant. But we're trying to solve the problem of having a fast data path in containers using technologies like DBDK. And then we're partnering with a company called Portworx to enable high-performance distributed storage for containers. And we're looking at enabling our non-volatile memory storage drives to serve as a distributed container storage cache layer. The way we're doing that is by enabling our storage performance development kit, which is a library similar to DPDK, to know about containers. And what that does is it creates a high-speed I/O channel for distributed storage applications inside a container. And right now we've got that deployed in the field at a leading genomics research institute that I can't disclose, and they're using it for their infrastructure right now as we speak. Any questions? Okay, so for industry standards, there's two standards bodies that we're interested in. There's the Open Container Initiative, the OCI, and the Cloud Native Computing Foundation. Intel is a founding member of both bodies, and we contribute to discussions around the file format that OCI is currently developing, the OCI file, the image format project. And in addition, we have the CNCF, which tries to drive innovation around the container ecosystem by identifying patterns and trying to develop code and sponsor projects to embody those patterns. And our role in the CNCF, aside from being a founding member, is that we run the CNCF data center, which I believe is here in Santa Clara. It has about 1,000 nodes in it now. We're scaling that up beyond 1,000 nodes. It is orchestrated with Stack-and-Netties and Kubernetes. We built the data center, we maintain it, and we also contribute code to the CNCF project, or we will be contributing code to the CNCF project. Questions? Okay. In the open source world, we're pretty committed to the open source ecosystem. We're one of the biggest contributors to the Linux kernel and to OpenStack. Linux kernel, top 5, OpenStack, top 10, I would say. We also contribute to Kubernetes and to CoreOS. I've already talked about Stack-and-Netties. And then we've been partnering with CoreOS and Mirantis to accelerate the integration between OpenStack and containers. The details about that are kind of vague, but it's an open source initiative that we're interested in, and we're trying to further the evolution of Kubernetes for that. And Intel operates on an upstream first process. When we develop new code, we first thing that we do is try to upstream it to projects. It's not always accepted. Usually it goes into a branch for a while and then it gets accepted. But we try to upstream code first whenever possible. And so in the container space, we work with CoreOS, Docker, and Ubuntu to do just that. And also we support the Canal project, which is a merger between Project Calico and Flannel. It uses the policy engine of Calico with the network capabilities of Flannel. This project is in a very nascent stage. It's very new, and so it's unclear exactly what Intel's role will be in it, but we are committed to supporting it. And beyond the cloud, there's two areas that go beyond the cloud, beyond the data center that we've identified could have potential uses for containers. That is high-performance computing and IoT. The Intel HPC Orchestrator is a scheduler for supercomputers and for distributed computing clusters. And it's part of the OpenHPC framework, and it is heavily based on containers. It uses containers to deploy codes and applications from service nodes to compute nodes and supercomputers to solve the dependency problem. If anybody has ever worked in an HPC environment, you know that the systems you develop your code on are usually completely different than the systems that you run your code on. So we think containers could help with that. You don't have to make sure somebody installs a certain library on a gigantic supercomputer or something like that. It just carries the dependencies with it. So we feel like that'll help enable faster deployment of applications on HPC systems. And lastly, our Internet of Things group is using containers in a big way to create a formalized mechanism, a standardized mechanism, by which containers that run the control software for embedded systems, whether it be a robot or a drone or something like that, even a smartwatch, can push a container down from the cloud in a way that the container knows what its dependencies are, and the devices can advertise what their capabilities are, and the cloud can match this up and deploy containers through something like Kubernetes or whatever in a standardized way. Any questions?
So with regard to this IoT aspect that you're looking at, does that focus on matching manifest? A manifest of functionality that's available from the application and a requirement set?
Yeah, what the scenario that we're looking at here is, so you have a mobile system, say it's a smartwatch, and you have a building which we'll consider a management domain. And this building has a Wi-Fi network and a data center. And this building wants to maintain the right temperature to make everyone comfortable wherever they happen to be. When you enter the building, your watch advertises to the cloud, I have a thermometer. So the cloud then pushes a container that has an application that can read the thermometer down to your watch. It knows about any web services or whatever that go on inside that particular organization. That can talk to the HVAC system. And it communicates the temperature where you are and your location. Say you're in conference room 132A, and it's too hot. It can communicate, it uses that container to read the temperature in that room, sends it up to the management system. The management system tells the HVAC system, hey, dial down the temperature in that room. And then when you leave, the container disappears from your watch.
Okay, that's important. The other question that I have to ask with regard to that is, when you've taken that information and you have identified that to the system, is there some mechanism that's involved in locking that down as opposed to having spurious information appear?
Right. Well, so what I just
Can you repeat the question?
Yeah, the question that was just asked is, based on that, how do you lock the information down? And I'm guessing you also want to know, how do you make sure that you're not pulling information off of someone's device that they don't want pulled off of the device?
Correct.
How do you guard that when it's in transit, when it's in storage?
Well, it's gonna be encrypted in some way, shape, or form.
Right.
Okay.
This is in the design phase now. This isn't Intel saying we've got a product and we're going forth with it. This is an idea. But a part of this design is an opt-in mechanism, such that you would say, when I walk into a building, they can use the temperature, the thermometer on this watch, but not the GPS or whatever. Because I don't want them to track where I am, but sure, they can get the temperature, I don't care. And then we would have to develop a whole bunch of policy and management around how we inform you, how you inform us being whatever management domain it is.
But
How
you
we
could also
encrypt it.
use beacons to provide that alignment too.
Yes, yes.
Okay.
Mhm.
Thank you.
Quick question on the
Yes.
stack, on the stack lattice. So you mentioned about the container in VM in container. So you said the container image for the VM in the container,
The container image for the VM container.
right?
Yes. Well, so what Stackanettes proposes to do is take all the pieces that are required to deploy OpenStack in an environment. If you've ever deployed OpenStack, it's non-trivial to do it in a way that actually makes sense for an entire organization. So what Stackanettes proposes to do is say, if you've already got a container orchestrator, such as Kubernetes, you can just take these set of images and deploy it in your environment, have Kubernetes figure out where to put them, and all of a sudden you've got OpenStack services. So that if you need to spin up virtual machines alongside containers, either on the same box or on different boxes, whatever, then you can do that easily. And the reason we did that is because a lot of people want bare metal containers, but a lot of people also have virtual machines. And the process of migrating applications from virtual machines to containers is sometimes non-trivial, especially if they're legacy applications or what have you. So most organizations that we've seen have virtual machines, whether it be OpenStack, VMware, whatever, alongside containers. So what Stackanettes proposes to do is to just make it easier to manage your OpenStack infrastructure and use the same orchestrator that you would be using for containers, so that if you decide to go full bare metal one day, you just turn on your OpenStack containers.
Okay, thanks.
Anything else?
In one of the previous slides, you mentioned you're using Project Calico for policies. So, what are the benefits of it compared to using, say, Project Control of Cisco? So I believe using Project Calico.
Well, it's not so much that we're saying that Calico is the better choice than Contiv. We're also partners with Cisco, and Contiv is a pretty important thing. We're not trying to make that assertion. We're just trying to say that a lot of people see a lot of downsides to using Project Calico. And a lot of people say that they wish Flannel had a better policy than them. So Canal was created to merge the two, to make the networking in Calico more palatable to people and to provide policy to Flannel. All we're saying is we're supporting that project. We're not saying you should use Canal or Calico or Flannel or whatever.
Some point in time you say that you have a high performance storage, and over there you use the term we have high throughput IO channel segmented. Can you explain the technology that is being used?
I'm sorry, could you repeat that?
Yeah, so you said that you have a high performance storage, right? Which
Mhm.
uses NVM. So in that same slide, you made a reference that you establish a high throughput channel, right? So
Uh-huh.
can you explain the technology behind it? How it will be much faster than normal storage?
The technology behind it is I'm sorry, the question was, what is the technology that you're using to establish a high throughput I/O channel for distributed storage? And the technology is pretty similar to the DPDK, in that we're just trying to eliminate system calls, copies within buffers in the kernel, direct access to the hardware from user space. That's the main point. You could see the SPDK as literally DPDK for storage.
That means still the connection between your storage system till the box will be as it is, and after that you have your channel.
Yes.
Thanks.
Anything else?
Yeah, you got these slides online somewhere?
We will
We
need
post it on
to.
Meetup.
And also we are recording the session, so we'll post the video also.
Cool. Okay.
Well, thank you very much.
If you want to take a break quickly for 5 minutes before Shirley can start this talk on